Ladies and gentlemen, hello. Today is 9th of December 2025. The Kyiv time is 20 and 3 minutes, 20 hours and 3 minutes. And now we start the next report, which will be presented at Belgrade seminar, more precisely the Belgrade Symposium, which is held every year in Belgrade, and in this year I'm online participant. Yes, I have an online participant. Okay, at this symposium with my postgraduate students. One of them is Zarina Kovba. Okay. Now I will start the report with our general report. For all who are listening now for me, I recall that this symposium will be held on 12th and 13th of December. So on this Friday and on this Saturday. Our report is called On Prime Ends Extension for One Class of Mappings. Recall that D is a domain in Rn, that is, D is an open and connected set. You can see on the picture the pre-image domain D and the mapped domain D prime. The first domain and the second domain are in the space Rn simultaneously. In the next picture, we recall you some definitions related to the modulus of families of paths. Recall that a path is a continuous mapping of an interval or a segment in Rn, and the length of the path is defined as a supremum of the sums of this type on the picture. Here the supremum is taken over all partitions by the points tk of the interval. Precisely segment. Interval is open, and this segment is closed by the definition. In what follows, rho is a Borel function, so a function rho is called inadmissible for a path family gamma big if the relation 2 holds for any path gamma small of the family gamma big I mean locally rectifiable paths, because for non-locally rectifiable, the length of the path and the integral may be not defined. Let P be a fixed number greater than 1, then by the P modulus of gamma big, we mean the infimum of the integrals in the right-hand part of 3. Here on the picture, you can see the path family gamma big and the modulus of gamma big is represented as some real valued function of gamma big, which is called P modulus. By the triple gamma EFD, we mean the family of all paths are right here continuous curves, but the name curve is assumed that curve is always continuous. So I'm made to say without of the word continuous. So once more, gamma big EFD denotes the family of all paths joining two sets F and E in a domain D, as in the picture. Let X naught be a point of D dashed, where D dashed denotes the closure of D. So D dashed is the union of D together with its cluster points. And by the Bx naught R, Bn, Sx naught R and Si, and A, X naught R1, R2, we mean the ball, unit ball, the sphere, and the annulus at the corresponding center with corresponding radii, respectively. Let F be a mapping and n bigger than 2 and Q be a Lebesgue measurable function such that Q vanishes outside of F from D. Let gamma F Y naught R1, R2 denotes the family of paths gamma such that F from gamma belongs to this family of paths. Namely, F from gamma A belongs to the sphere S Y naught R1, F from gamma B belongs to the sphere S Y naught R2, and F from gamma T belongs to the annulus A Y naught R1 R2 for any T bigger than A and not greater than B. We say that F satisfies the inverse Poletsky inequality at Y naught if the relation 5 holds for any corresponding R1 and R2 and for any eta satisfying 6. We see on the picture the illustration of the mapping which satisfy 5 and 6. So in the a priori image, we have the family gamma F Y naught R1, R2, and in the image under the mapping F, we have the family of paths joining the spheres centered at the corresponding point and of the corresponding radii. Recall that some mappings, some known classes satisfy the relation 5 and 6. In particular, quasi-regular mappings with the corresponding functions Q, which is calculated as follows. This is the first remark. The second remark that more general classes of mappings, say Sobolev mappings, which are the mappings which have the first order partitional derivatives which are locally integrable in the degree n, which is denoted by the W1n log from D. So the mappings of such classes satisfy the relation 5, 6, provided that the corresponding function KO, which is defined as below, is in the class of L n-1 log. There are functions which are integrable by Lebesgue in degree n-1. The following definition related to prime ends. So the report is devoted to prime ends generally. In what follows, omega small is an open set in Rk where k between 1 and n-1. A k-dimensional surface is a continuous mapping of this type. In particular, if k equals to n-1, we say surface without of the prefix k-dimensional. So k-dimensional, where k equals to n-1, is called surface simply. Jordan surface is a surface without of self-intersection. In what follows, we also write sigma instead of sigma from omega, sigma dashed without of sigma omega dashed, where this line, as usually, denotes the closure, as I have said above. And d sigma denotes sigma dashed without of sigma from omega. A cut sigma is a Jordan surface which split D. So D minus sigma consists of some number of components, more than one. Besides that, the relations 10 hold. For example, this line is a cut from D. Why? Because if D is this domain, then this cut divided a domain D on two components. What are these components? This is one component, so these points may be joined by a path, and this is two components, so we may join 2 points here as well. But if we have this point, and we have a path, so this path intersects this cut. This is a definition of a cut. In this picture, we have also the definition of the chain of cuts. The sequence of cuts forms the chain if the conditions I1, I2, and I3 hold. In this picture, we also have the correspondence between chains in the prior image and chains in the image. In particular, this sequence of cuts corresponds to this sequence in the image under the mapping F. Similarly, for the chain Km, this is kappa, kappa M. Maybe say Km or kappa M without of the difference. This is the chain sigma L or sigma M. It maps under the mapping F on another sequence of cuts in the image under mapping F. The image in this case is a ball or a disk at the plane. Two sequences of cuts are equivalent if domains which are formed by these sequences are equivalent in the following sense. Dm contains every dk prime except finitely many k, and vice versa. So at the previous page, if we have a cut sigma m, then a domain dm is a small domain which is formed by this cut on the domain D. These domains dm small are increasing sequences of domains. What is this? D1 contains D2, contains D3, contains Dm, etc. Similarly for any chain. For example, for the chain formed by the kappa M sequence. This chain of domains is a domain chain G1, G2, Gm, etc. So two sequences are equivalent if the first sequence contains all another sequence and vice versa. The another sequence contains the first. Here is a draft mistake. Here dk prime contains all dm must be. Dm, not dk prime. Here it would be dm as here. And is defined as equivalence class of chains of cuts in D. And K big is a prime end if and only if firstly K is an end, and secondly the relation 11 holds for some a continuum C in D. We see on the picture some continuum C. So if we have the sequence sigma 1, sigma 2, sigma m, etc., we're joining C with sigma m by a path. So we define the family of paths gamma C sigma m D. So if the modulus of families of paths, which is defined above tends to 0 as m tends to infinity, then and k is a prime end. Let us consider the following definition. DD is locally quasi-conformal. So this is the boundary of a domain D. as in the picture. So the boundary for domain D is locally quasi-conformal if and only if any point x0 of DD. For this point, there is a neighborhood U of this point and a quasi-conformal mapping phi of this neighborhood as in the picture. So this is a point, this is a neighborhood. So phi maps phi maps the intersection of DD with a neighborhood U onto the half ball. This is also some draft mistake. Here it must be D with intersection of U, not DD. This D is not must be here. Once more, phi maps D with intersection of U onto the upper half ball in Rn, centered at the point phi from x0. Here also D is not required. A domain D is regular if D is bounded and D can be mapped quasi-conformally onto a domain with a locally quasi-conformal boundary. If we denote by dp prime the completion of a regular domain D by its prime ends, then we may define the metric rho naught between prime ends P1 and P2 in this space dp dashed, which is defined by the equation 11. The 11 assumes that we know this quasi-conformal mapping G0, which maps D0 onto a domain D. So if we have some mapping of D onto another domain with a locally quasi-conformal boundary, this picture is not good because it relates for another notion for domains with a locally quasi-conformal boundary. But similarly, we may define the mapping G0. So if we have D with a bad boundary, generally speaking, we may map this mapping D onto D0, and we may prove that every prime end here corresponds to some point in the good domain. So this point is called G0 tilde -1 from P1. Similarly, for a prime end P2, we also have the corresponding point, and the distance between prime ends P1 and P2 means the Euclidean distance between the corresponding points in the good domain, in the domain D0. Prime ends extension for quasi-conformal mappings. This is known fact for mappings which were studied by Nyaki. Given a mapping FD from D into D prime, we set the cluster set of F at the point x naught x as following. Similarly, we may define CFDD. So this is the image of the boundary under the mapping F, but the mapping F may be not defined on the boundary. This is analog of the mapped set of the boundary, where F is not defined on DD, generally speaking. Theorem 1. Under quasi-conformal mapping F of a domain D naught with a locally quasi-conformal boundary onto a domain D, there exists a one-to-one correspondence between the boundary points of D naught and the prime ends of D. Moreover, the cluster set CFB coincides with impression. Impression is defined by this formula of the corresponding prime end. And what is about prime ends boundary extension for more general mappings? Recall the following definition. We define the chordal distance between 2 points x and y in the extended space Rn dashed, which is Rn together with infinity, by the following rule. If we have some points x and y, then we see the projections of these points in the Riemannian sphere centered at the point E n plus 1 over 2 and of the radius 1 over 2. So the projections of x and y are points P from x and P from y. This length, the length of this segment, is called a chordal distance between points x and y. There are precise formula of chordal distance between points. Further, the closure and the boundary of the set are understood with respect to the chordal metric H defined as above. We say that DD is weakly flat at the point x naught if for every neighborhood U of x naught and every number P bigger than 0, there is a neighborhood V of U of the point x naught. So V is contained in U, and simultaneously V is a neighborhood of x naught, such that the relation 13 holds for any continua E and F in D intersecting DU and DV, as in the picture. So we have some point x naught, we have an arbitrary neighborhood U of x naught, we have some smaller neighborhood of x naught V, such that V is contained in U, and we have two arbitrary continua E and F intersecting DV and DU. So the modulus of families of paths may be greater than P. So modulus of families of paths, in fact, tends to infinity because P is arbitrary, infinitely big number. This definition is geometric and means that a domain D is a domain without of cuts formed, which are formed in the point x naught. So this is not be, for example, a disk with a cut. A disk with a cut is not a domain with a weakly flat boundary. Assume that d prime minus CFDD consists of finite numbers of domains, where any domain di is a regular domain in the definition mentioned above. Besides that, these domains are disjoint, and we set rho g from xy equals to 0 if x and y belongs to this set. Also, rho g xy equals to 1 if one point x is from DGP and another point is not does not belong to DGP dashed. So rho g is a metric which is defined here for a domain DG, where we take x and y from DG, we use the metric which is defined as above. But if x and y is not belong, do not belong to DGP, or another situation, one point x is belong, but another does not belong, then this metric rho g equals to 0 or to 1 respectively. By the definition, this is at least a definition of rho g. It is not a statement. Then rho g is a pseudometric on this space. I advise to see the definition of pseudometric in the literature. For example, in the book of Kuratovsky, Topology. Now we set a rho from x5 as follows. Besides that, we may show that rho g star is metric, where rho g star is defined as here. Also, we may show that rho is a metric, where rho is defined as here. Theorem 2. Let D and D prime be domains in Rn n bigger than 2, and let D be a domain with a weakly flat boundary. Suppose that F is open discrete mapping of D onto D prime, satisfying the relation 5, 6. In addition, assume that the following conditions are fulfilled. 1. For each point y naught in D prime, there is R naught, such that for any R1 and R2, with this condition, there exists a set E in R1, R2 of positive linear Lebesgue measure such that Q is integrable over sphere centered at y naught of the radius R. Secondly, D prime without of CFDD consists of finite number of pairwise disjoint domains D1, D2, etc., Dn, any of which is regular. And f minus 1, the prime image of this set, is nowhere dense, then the mapping F has a boundary extension of this type, which is continuous in the corresponding set by the metric rho defined as above. Moreover, F dashed from D dashed equals to this space. Thank you very much. So the report is not simple, but I think Zarina must make the very good report on the conference. It's over for today. Thank you very much and good luck. Слава Україні!